Yeah. Well, we're halfway there.
Yeah. I mean, at work, we have bi-weekly sprints. So the second week is a little more intense for us while we have reviews and finishing up tickets and all that. So yeah, this is our
Mhm.
second week of the sprint.
Got it. Yeah, I know how that can be. Like crunch periods. I've gone through them myself. Yeah.
Mm-hmm.
Always a charm. Hey, Amelia, I see you coming in. Welcome. All right, so let's hey Amelia.
Yeah, hey. Hey Ramya, hey.
Hey, Amulya.
Okay, so we're starting the chapter 3.
Yeah, I was just about to say that, but I just saw you were about to say something, so I just okay, so yeah. So this one, it was kind of like an interesting chapter. Let's just go through it. So I think this one is mostly about like actually creating like a data engine. You know, they kind of build one from the ground up.
Yeah. So how useful do you think this discussion would be? I know it makes us better engineers if we understand how internals work. But I don't know if it's going to be very useful diving deep into how the data structures what data structures databases are using. But
On a high level, I think we should understand these what are SST tables and by B trees, because I've seen people ask like, okay, what is a B tree? Can you explain it? Or what is an SST table? Or what is compaction? Explain it. So these not going to nth level of degree but of details, but having what is the difference between these data structures also comes up in the interview.
I remember studying this as a database course in my grad school. But I was wondering why we are reading this then, and I'm wondering why we are reading. Anyway, okay. But yeah, it's at a high level. Let's not go too deep. We took like almost a month for the second chapter, so let's not go that deep. But yeah.
No, I agree with you. I mean, I think from the last chapter, we can probably have a little less discussion for each section, and then maybe more like work on some, the engineering aspects or like the practice. But that said, like I agree too, like I kind of feel like for me, I don't really want to skip anything because then, I kind of feel like it's a hole in my own understanding. So I'll probably just keep reading anyway, like, for myself, like outside of this, right? Like I'll just try to like brush up on this. But if people do want to skip the chapter, I'm totally okay with that as well.
Let's go. I mean, let's finish it. Like if I think some understanding is, I'm not suggesting that we should skip it, but we probably don't need to, go really, I mean, discuss much, just focus on covering the breadth.
Okay. Well, yeah, like I said, I felt like this chapter was pretty much, about like actually creating a database, like how does it work? And, I think this part of the chapter here was kind of like demonstrating how you could set up your own database using just something like bash, like inside your Linux command line tool. You have like basic set and get functions. And then, you're basically kind of entering two arguments. One would be the key and one would be the value. That would be what gets set to your in-memory database. And then get, this is the same thing. This is just a grep command. Then you're passing it to the sed command and you're searching for the key and you're searching for the last entry. That's what the tail command means. There are two types of storage engines that they go through in this chapter, which was the log structured storage engines, and then the page storage engines, such as a B tree. So yeah, let's go through it. So the main thing about, like, I guess how he's implementing this is kind of like, he says that the underlying storage format is very simple. It's a text file. And so that's what constitutes this database. If you look at the values, they have kind of like a JSON syntax, but it's not really, JSON. It's just text. It's more like a CSV, but he's ignoring the escaping issues. So I highlighted this part that says every call to DB set, right? This function here, basically appends to the end of the file. So if you update a key several times, the old versions of the value are not overwritten. So he preserves, pretty much like all the data, right? Which is kind of like in the same vein with the database. You don't want to like just overwrite data. You want to save new data. Has anybody else heard this term before? Like just, some people talking about it, like to you at work or whatever, right? Like you don't want to delete data. You want to just continue to append. You don't want to overwrite.
We have server logs, which are always append, and we don't overwrite. Every new session, we create a log, and then these logs are compacted and added someplace until the retention policy for that S3 bucket is probably 5 years from today or something.
Yeah, correct. So yeah, I was interested in why this person chose append, but there are several reasons for it. So one was to append.
I think we chose to append for faster access, to just not deal with anything else, just append and reduce the latency of the operation.
The other thing is, and I'm sure we'll get to it, right? Like, but if you append to any data structure, like, array or linked list, it's usually the fastest operation, right? It's O1. In that, the big O just basically means like the number of steps that it takes to do the operation. So if this number of steps are just kind of finite, then that would be considered a constant operation. Whereas like if the steps just keep increasing as the data structure, itself increases in, size, then that would be considered ON. And then there are like other, like things that go beyond this, like ON squared and ON cubed and ON factorial, but nobody uses that in real world ON factorial. That would not be like an actual business application. So here, append is a cheap, that's what I want to call it, like a cheap method, in that like it just appends, it's easy. So if you update a key several times, the values are not overwritten. You just need to look at the last occurrence to find the latest value, hence the tail-n1, basically look at the last item in the text file at line 1 and get it. So this is kind of like the simple database. It says that, so this is another thing, right? Like imagine that you had to build a database. That might be a system design question, right? So like, how do you get started, right? And I think he does a pretty good job of just starting with the basics, right? The set and the get function. And then he builds on it. And so he says that the dbset function has good performance for something so simple because appending to the file is generally very efficient. Similarly to what dbset does, many databases internally use a log, which is an append-only data file. Real databases have more issues to deal with, such as concurrency control, reclaiming disk space, so that the log doesn't grow forever, and handling errors and partially written records. But the basic principle is the same. So like I was thinking about this too, like, because we talked a little about concurrency, right? When you make a database, it's something that you want to think about, like how will you handle concurrency in multiple threads, right? So you don't want to like make multiple writes to the same database with different threads. So he kind of says that concurrency wise, and I think he says a little bit later, you want to just allow for one time to set, but you can have many threads get. And I thought that was kind of cool. I've also had issues like when I started learning AWS, like I would have, some PHP servers running on there or Node.js servers. And there was a log that just kept, running every single time there was a new page request, and that log started to grow and grow and grow. And then eventually I started seeing like you are low on memory every time I opened up the system, and I would say, oh man, some of these logs. So I had to go and clean them out. But I found some of the stuff in this chapter pretty useful about compaction and all that. I've never done that, and that's not my job. I'm more of a front-end developer, but like I wanted to just kind of learn. So I was jumping into that part. So I guess like logs, like everybody here pretty much, I would assume, knows what a log is. Did you have something to say, Amelia?
No. So basically I was gonna say, like Ramya was also saying about S3, right? So S3 offers this ability. You just define storage policy, S3 bucket policy. So to basically archive older logs and kind of store them in an efficient manner. So you can have a retention policy after that. You can either delete them after a certain point or have them archived and in a storage efficient manner. So you don't pay, because your storage costs grow as time passes, right?
Mm-hmm.
So I think S3 offers that out of box.
Yeah, and I think I might have been using a combination of S3 and EC2. I think in EC2, I don't remember exactly. It was sort of the beginning, like when I was doing it, that like I had these issues with logs. So, but it'd be good to go back and check. I feel like this time around, I'd probably know like what I was doing a lot better. So let's see here. He just kind of like talks about logs and how that some logs are not, human readable, which I thought was interesting. Some are just binary and intended for other programs to read. So here he mentions that get has terrible performance if you have a large number of records in your database. Every time you want to look up a key, the get function has to scan the entire database file from beginning to end, looking for occurrences of the key. So here, another data structures and algorithms, so this operation is ON in terms of steps, because you have to keep scanning until you get to the end of the file for each record. And if you double the number of records in your database, then that lookup takes twice as long, which is not good. So in order to efficiently find a value for the database, you need a different data structure, which is an index. And so he kind of talked about how an index works here in this diagram. And he talked a little bit about keys and byte offsets. So the idea is that the key represents like the place, the entry point for the value that you want to find. And then the byte offset just basically starts the address, like which address it starts at. So if you have this index, basically you can go to the byte offset. So here we have 0, and then here we have 64 to get to the key and then proceed to get its value. So that's how, this index can help, speed up the operation of finding a key value pair. I see that you just said something, Karthik. So it says mounting an S3 bucket on EC2 is possible, but not a viable approach, as NF mounts work better like EFS, but typical easy way is to do EBS volume. Okay. Do you want to add anything? Or?
No, I just didn't want to derail and take the discussion elsewhere. That's why I was like adding in the chat. Yeah.
Got it. Okay.
Yeah.
All right. So here he was kind of saying that an index is an additional structure that is derived from the primary data. So many databases allow you to add and remove indexes, and this doesn't affect the content of the database. It only affects the performance. So this is like something that just lives on its own in memory, elsewhere. And when he was talking a little bit about disks and memory, I thought, wow, okay, this is pretty cool just to kind of know like what's going on at the low level. So he said it's hard to beat the performance of simply appending to a file, which we discussed, because that's the simplest write operation. Any kind of index usually slows down writes because the index also needs to be updated every time the data is written. And so this is kind of a trade-off that you would need to be aware of when you pick, your own database engine. Well-chosen indexes speed up read queries, but every index slows down writes. So you don't want to index everything by default. You just want to choose, like which indexes give the application the greatest benefit without introducing more overhead or more, steps than necessary. So how many people here know what a hash is? I'm sure you do. Anyone unfamiliar with it? So a hash is basically just the dictionary, or, in JavaScript, that's an object, right? It's a key and a value. So in a hash index, it says that key value stores are quite similar to the dictionary type that you can find in most programming languages, and it's usually implemented as a hash table. So in my mind, a hash map just basically means like, array backed, right? But some hash map implementations are binary tree, binary search tree, or I guess just binary tree, like implemented, BST implemented, because they're easier to like look up, and you get like a certain O log n guarantee with the BST in terms of retrieval. But yeah, that's where this chapter starts to become a little bit more difficult in terms of which implementation you use, like for the hash map. So it says, since we already have hash maps in our memory data structures, why not use them to index our data on disk? So he just basically says that the simplest possible index strategy is this: keep an in-memory hash map where every key is mapped to a byte, as we discussed here. And whenever you append a new key value pair to the file, you update the hash map and reflect the offset of the data you just wrote. So like as you write the data, you append, and then you update the key if necessary, if you're adding to the same key about the new offset. So that way it finds the new version of that key. And you can read that value. Any questions so far on this implementation so far? Okay. So let's go on to next area. So this approach so far that we've just kind of gone over, there's an application called Bitcast. And I actually wanted to pull that up because I didn't look it up last night. I don't know if this is still around, but yeah, I guess it still is. So it's written in Erlang, and it's considered, a simple application for retrieving key and value data in a log structured hash table. So might be worth kind of just going and taking a look at this. It says that this is the default storage engine in React. And I've never heard of React. Has anybody here used this? Maybe it might be too low level, as we'd kind of discussed.
I mean, I use a similar one, but not exactly this. There's something called RocksDB. It's a low-level key value store. I used it to build for a hackathon, like some kind of a tiny URL kind of thing, like a Bitly thing from my previous company. But yeah, you can implement these things embedded. This is just like library. You can embed it in your Erlang application with the dependency, and then use it like a database, like key value store. Although it's not completely distributed here, but at least you can store it in the storage.
So like very tiny storage, right?
Well, it can be big enough too, because end of the day, it's all key value, right? As long as there is storage in your wherever the application is running, it should be fine. It doesn't slow down these things because they just fetch the key and the value and they are stored locally. It's not truly distributed. But the only problem is, for whatever reason, your machine goes down, your database completely goes down unless you don't back it up.
Got it. All right. Looks like Uber's using it. And I was thinking this in the back of my head, would this make sense for like a simple app, like game app or something? And I see Riot Games here. So yeah, there's some of the customers. Oh, Best Buy uses it. I wonder why. Okay. All right. So here he says that Bitcask offers high performance reads and writes subject to the requirement. And Bitcask is basically what we just kind of went through. Like as a example, it's kind of like that. The hash map is kept completely in memory. All the keys must fit in the available RAM, and the values can use more space than there is available memory because they can be loaded from a disk with just one disk seek. So this Bitcask application uses both the in-memory and then the disk as well. Okay, thanks for the link. I'll put this, I'll open this in a sec. So if the part of the data file is already in the file system cache, a read doesn't require any disk IO at all. So here I said that, or I highlighted that Bitcask is well suited to situations where the value for each key is updated frequently. So, if you have URLs of cat videos, I guess he was saying, then you can also have, so that would be like the key, the URL itself, and the value may be the number of times the video was played. So in this workload, like when you have a lot of URLs, maybe from YouTube, you know that there are going to be a lot of writes to your database, but not too many distinct keys. You have a large number of writes per key, but it's feasible to keep all keys in memory. One more thing I see in the chat. Okay.
So the by nature of these DBs, right? So they cannot be used in a distributed fleet, right? If you have multiple, like let's say you are trying to host some service like the Bitly or like tiny URL kind of stuff. So since the data is localized to a single machine, you cannot really scale it up to multiple servers, right? So
yeah,
that's
that's an issue with this particular system, right? It's good that you're thinking about it.
These are embedded databases, right? Like think of a scenario, you have built an IoT system, right? A small IoT system, you want storage, some kind of a persistent storage on the machine itself. Like these are like some tiny footprint databases. It's not huge. Although having said that, this implementation can be distributed. You can take it, add bells and whistles, like, you can have Apache Zookeeper on each machine, because that's the coordination kind of a service. And then LevelDB is from Google's implementation, right? Jeff Dane implemented this way back, I think with a few other guys. And they have extensively used in a lot of services as a distributed thing, right? So this is a foundational thing that's been exposed, but yeah, these can be made distributed. Like, by adding other components to it, scheduler, and like, making sure the synchronization happens across nodes and stuff like that. This is a really base level thing, right? On top of it, there are some other implementation. I'll send you some other links which helps them become distributed too. So RocksDB is Facebook's implementation of key value store. It was rebuilt, if I'm not wrong, completely in C++. LevelsDB was in C, so there was some added performance benefit in RocksDB over LevelDB. And this all about this again goes back to the discussion that you guys were having, B tree versus LSM tree. So these are all some of the examples of LSM tree kind of a structure.
So Zookeeper, so you mentioned about something. So the Zookeeper is a service that does DB sync across multiple nodes.
Not just DB, it can be any distributed systems, right? Even services too. Apache Zookeeper, it's a synchronization service. Let's say that you have like 5 nodes, right? Even for example, if you're running some kind of a service, messaging system and stuff like that, any middleware too, you can do synchronization across these nodes too, right? It's basically a synchronization kind of a service. It's Apache open source thing. If you notice, a lot of big data systems like Hadoop and everything, they use Zookeeper by its nature, right? That's the whole synchronization mechanism that they have across nodes, replicating data here and there based on the quorum.
So you're saying hypothetically we could use this on a scaled out fleet.
Yeah.
By doing enforcing the synchronization by third-party services like Zookeeper.
Yeah, it's on top of it, you can always, so if you notice every database, even for example, MongoDB or Cassandra, everything has some kind of a key value store underneath them, right? Probably MongoDB a little bit different implementation because it stores the whole document. But the point is, these are the storage engines, if you will, and every database has the storage engine. Even MySQL or Postgres, they all have the storage engine. When we choose MySQL, InnoDB engine, so those are specific implementation of the storage of the database, how it writes on the disk and how it does the compaction and stuff like that. So this is an example of a storage kind of a layer for the database. On top, you can build other capabilities.
This is really interesting. I'm actually going to send this link over in Discord. So let's put this in the chat, and then also put all the other links today from the discussion in the chat as well. All right. Good discussions so far. So basically, yeah, this is kind of like a very simple database. And again, it's key value. I think like that's kind of how stuff gets built in the beginning, like when people are trying to create their own from scratch. The next issue is that basically when you keep appending, like you are making the file bigger and bigger and bigger, and eventually you're going to have an issue with disk space, right? So one way to keep the file from getting too long and too big is to use the term compaction. And that just basically means throwing away the duplicate keys in the log and keeping only the most recent update for each key. So in this picture here, he has, the following keys: mu, per, mu, per, yawn, per, mu, right? And so you could think that this was appended, 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 and so on until we got to here. Yawn, per, and mu would be pretty much the last, updates for all 3 of those, keys. And so he just compacts this into yawn 511, mu 1082, and per 2108, because these are the latest values for those keys. And then the rest of the data is unneeded. So compaction often makes segments much smaller, assuming that key is overwritten several times on average within one segment. And we can merge several segments together at the same time as performing the compaction. So, segments are never modified after they've been written. The merge segment is written to a new file. And then I wrote a highlight here that the merging and compaction of segments can be done in a background thread. So this means that it's not while the main app is, providing reads or whatever. Like this can probably be done either in the background or like offline when there are no requests going on. And so if there are read requests to this database, we can just serve the old file, and that might be slower, but once the compaction finishes, then things will be faster and we can use the latest segment file. So here he just says that when merging is complete, we switch read requests to use the new merging segment instead of the old segment, and the old segment can be simply deleted. And I think this is a pretty common pattern, like use old until the new is available and then remove the old, right? Like a caching strategy. So this is kind of like a good strategy with compaction. Does anybody here have any issues with compaction or like still not understanding it? Okay. All right. So here's another diagram. And this is one data file segment. So you can think of this as like a block. Then this is another one. And so taking these together, we're basically, again, compacting down to like the latest values. So you can see pers here, mus here, scratch, that's the latest value for scratch here, 252. And then yawn was only updated here, so 511. So this all gets compacted down. Each segment now has its own in-memory hash table, mapping keys to file offsets. So you still have that in-memory hash table that has to like continue to get updated with the file offsets to be able to find where this is located in that text file. In order to find the value for a key, we first check the most recent segment's hash map. And if that key is not present there, we check the second most recent segment, and so on. The merging process keeps the segments small, so lookups don't need to check any hash maps or many hash maps. So maybe later we can come up with a system design if people want to try. And one facet of it could be just like compaction, how to, take some file that might be text and get it down to like a simpler version. It could be like some code to implement, or it could be like homework if you want to do it that way. Let's see here. So then, like you said, lots of detail goes into making this simple idea work in practice, right? Just even though this is such a simple concept, it's still, there's a lot of work that needs to be done. Even in just terms of like file format, being able to delete records, recovery, partially written records, concurrency and control. Like he says, it's faster and simpler to use a binary format that encodes the length of the string in bytes, followed by the raw string. If you want to delete a key and its associated value, you have to append a special deletion record to the data file, sometimes called a tombstone. And this helps basically the merging process discard any previous values for the deleted key. So these are like tweaks, like fine tunements. If the database is restarted, then the in-memory hash map is lost, right? So if you want to restore the segment hash map, you need to read the entire file again, right, from beginning to end, and noting the offset for each recent value as you go along. And so if a server crashes, right, this process could be long and painful. So Bitcast speeds up recovery by storing a snapshot of each segment's hash map on disk, which can be loaded into memory more quickly. So snapshot is kind of like a database save of what that file looked like. And then, like you can pull that out and go, okay, this is how the project looked. And then based on the diff, you can change the file so that the file is more ready to go, or the hash map is more ready to go. You want to check for partially written records. I think this kind of goes into that ACID, philosophy where, you don't want to be writing at the same time. So Bitcast files include checksums. You don't want to have halfway, partial records or corrupted parts of the records in your database. So this stuff allows those parts to be detected and ignored. Concurrency also plays into ACID. Writes are appended in the log in a strict sequential order, meaning you can't have more than one thread, like, updating the file at the same time. And he says that down here too. Common implementation choice is to only have one writer thread. Data segments are append only and otherwise immutable, so they can be read concurrently by multiple threads. Karthik, I just wanted to ask you too, right? Like you said, you had a lot of work with Go, or you've been using Go. Did you use it for this? Because I think this might be a good reason to choose something like Go, right? If you're creating your own database.
No, I didn't use this. I did this on C++, but I use Go for building a totally different thing. I was building just-in-time kind of analytics, where it was just getting a lot of data. Like it was a customer survey kind of a tool, like Qualtrics and of stuff. So it was building some analytics for customers, and it was slow, right? There was some calculation on the fly, but like somewhere like too dynamic in nature. So I use Go for mainly concurrency to do a lot of computations on the fly behind the scene. But it was for API, so yeah, totally different.
So the part that you used for concurrency was, you said like go grab a whole bunch of stuff, right? So you had concurrency for a lot of reads. That was kind of like why you chose it? Yeah,
there were a lot of reads and computation on the fly, smaller computations on the fly. In Java, generally threading is not a good practice. If you build on top of any API server or deploy it on a JDD kind of a concept, or even Spring Boot or whatever. So I couldn't really enhance and use the CPU cycles that we were deploying on. The cores effectively were not getting used. So that's why we pivoted to using some kind of a language which is going to effectively use all the cores and help me do computations on the fly without compromising on the memory too much.
Got it. And that was Go, right? The Golang?
Yeah.
Okay. All right. Yeah. Just interesting to see this, again, in so many different places. Maybe a database should be implemented with Go. I don't know. That might be something to look into. So here,
do you know etcd?
No.
etcd is a key value pair that's implemented in Go. If you guys are aware of Kubernetes, underlying storage is etcd. That's implemented in Go. I mean, there are so many applications that's implemented in Go, which are open source, and we touch upon our day-to-day life.
This is the one you're talking about, right? etcd. I don't know if you can see my screen, or you might be muted.
Yeah, that's it. Yeah, that's a key value database, and it's distributed as well. It uses RAP protocol and stuff. Yeah.
Wow. Okay, this is pretty cool. All right. Okay, so any other questions before I go back? Actually, it is a study group. Okay. All right. So here he kind of starts, going into a new tangent for the chapter. He says that append only log seems wasteful at first glance. Why don't you update the file in place, overwriting the old value with the new value? And then you don't need to do compaction. But he says that append only design turns out to be good for these reasons, right? If anybody asks you why you would start off with an append rather and do all this compaction stuff, appending and segment merging are sequential write operations, which are generally much faster than random writes, especially on magnetic spinning disk hard drives. And to some extent, sequential writes are also preferable on flash-based solid state drives. Try saying that 3 times fast. So we'll discuss this issue further in comparing B trees and LSM trees. So we're going to get to that. So this is interesting to know. Again, I never really gone this low, so I don't know about magnetic spinning disk drives versus solid state disk drives and how it affects the database. But I suppose if I was building a database, I would need to know. So And it's nice to appreciate too, like if you understand this stuff again, as a user, like, okay, this is how much more performance I get out of this particular database engine than something else. So concurrency and crash recovery are much simpler if segment files are append only or immutable. You don't have to worry about the case where a crash happened while a value was being overwritten, leaving with you a partial old and partial new. So like if you have the append, you can just append again and you won't have partial files. Merging old segments avoids the problem of data files getting fragmented over time. But in contrast, the hash table also has limitations. The hash table must fit in memory. So if you have a very large number of keys, you're out of luck. In principle, you should maintain a hash map on disk, but it is difficult to make on disk map perform well. It requires a lot of random access IO, which is slow and expensive, and hash collisions can require fiddly logic. So hash collision is just basically like keys that have or the same index having the same key, if you save something to a hash table and it has, the hash spits out the same key, you're going to have to like do some kind of implementation to store maybe that key at the same index as a linked list or another array, or like maybe do some kind of like other ways to like avoid the collision. Otherwise, those two keys are going to point to two different things. That's not good. And then he says that range queries are not efficient. For example, you cannot easily scan over all keys between kitty 000 to kitty 9999. You'd have to look up each key individually in the hash maps. So that kind of concludes the section on just the append only. In this next section, we talk about like the ST tables and LSM trees using this kind of indexing structure that doesn't have limitations as the hash table does. Any questions so far on any of this? Okay. And if you have questions later or want to add to the discussion, you can always do that on the Discord or the WhatsApp or on the comments. They'll be fine. So here we talk about SS tables and LSM trees. And basically, the first part of this is that he's saying that each log structure storage segment is a sequence of key value pairs. These pairs appear in the order that they were written, and the values later in the log take precedence over values for the same key earlier in the log. But the thing is that the order doesn't matter in the key value pairs, right, of this file. So, if you want a sequence of key value pairs sorted by key, we call this format sorted string table, or SS table for short. Using this format, we can not append new key values to the segment immediately, since writes occur in any order. And so SS tables use sequential IO. And then he kind of goes over SS tables in terms of advantages and log segments, hash indexes. So merging segments is simple and efficient, even if the files are bigger than the available memory. So here he says that, like when you merge stuff together, it's more like the merge sort algorithm, where, like in merge sort, you just basically divide, like a whole long list of elements, and then you keep dividing until they're all like one-off arrays. And then the second part is you do a comparison where you check which index is bigger than the other index, or the value in the index is bigger. So like if this one's bigger, then you choose that goes to the new sorted array that results from the merge sort. So this value would go here first, then the next value would go next, right? So this actually would be lower. So this would probably go first, then this would go next. And I'm saying that because I think these things say handlebag, but I just realized that they're handbag and handlebars. So the point is that essentially, like, you're kind of just doing looking at your input files side by side, looking at first key in each file, and then copy the lowest key again according to the sort order to the output file and repeat. This produces a new merge segment file also sorted by key. So this is something that you can do, and this works better for compaction and merging. And so he asked, what if the same key appears in several input segments? Remember that each segment contains all the values in the database during some period of time. This means that all the values in one input segment must be more recent than all the values in another segment, assuming that we always merge adjacent segments. So that goes back to like this, kind of merge sort algorithm thing that he's saying. When multiple segments contain the same key, we can keep the value from the most recent segment and discard the values in older segments. So that's how you preserve like multiple keys. You just kind of choose the one that's more recent. And that kind of reminds me of like, the whole, I don't know if people have heard of this, but unstable sorts versus stable sorts. Is anyone familiar with that? Like what an unstable sort is versus a stable sort?
I think one preserves the order in which the keys appear, the stable sort, and the other doesn't. For example, merge sort can be written in a stable way depending on how you write the comparison.
Right. So like an unstable sort doesn't preserve, like the, it says that like when you have two keys that have the same value, stable maintains the position of the two equal elements relative to another, whereas unstable elements don't really do that. So here's kind of like a diagram, but essentially this is like the idea is that you maintain the position of two elements with the same. So like when you choose your algorithm, you want to know whether it's a stable sort or an unstable sort. So I think this is probably doing the same thing. It's using some kind of stable sort algorithm in order to choose the more recent segment. Then here, number two.
I had trouble understanding that point. So they're saying, first of all, what does it mean to have, so if you had a same key into, is that even allowed, right? Aren't keys supposed to be unique in a key value store kind of a DB? And then what? So second question is, I need to probably go back, read what is the problem they're trying to solve. So if it's a key value store, right, the keys are supposed to be unique, right? Isn't that the...
Keys are unique, but in each segment, the keys are, every segment, the key is unique. But if you look at multiple segments, handbag is repeated or something like that. So that's why when they are combining it, they want to make sure always handbag,
which one? Came first.
Oh, so when you're okay. So
that's the stability part, right? Which one is more recent in terms of the array?
Right. So there's some metadata involved, which kind of tells which one was inserted first and which one was inserted later. And
correct.
That's how it's maintaining the order.
Right. You need stability in order to keep, like
and sequence data, right?
Yeah, the data in sequence.
Okay, got it.
And I'll also link this as well. I was just starting to read it as you were. I'm trying my best to read fast and like understand like whatever the person who is writing something on their page or whatever is saying. But I think this one kind of does it here, like the Stack Overflow. So in an unstable sort algorithm, straw and spork may be interchanged, but in a stable sort, they stay in this relative positions because straw appears before spork in the input So it should also appear before spork in the output. So this, even though like, they've reordered it, apple, peach, straw comes before spork. And they can be interchanged in an unstable, but in a stable one, they stay the same relative positions. So then he says we could list words using this algorithm. Stable sorting by column 5, then 4, then 3, then 2, then 1. In the end, it will be correctly sorted. And then this is a radix sort, by the way. Then suppose we have a list of first and last names. We're asked to sort by last name and then first. We could use the first sort, stable or unstable, by the first name, and then stable sort by the last name. After these sorts, the list is sorted by the last name. However, the last names are the same, but the first names are sorted. So yeah, just have a read at this, if you want to kind of get like more information about stable versus unstable sorting. That makes a whole difference in terms of like doing, work further, like with ordered data. All right, so it's 8:23. I think we got a few more minutes, so we'll go through this and then let's see here. The next section, like he's kind of talking about, just again, these points, like what an SST has in terms of advantage over, the previous log segment with hash indexes. And so we kind of talked about merge sort being kind of like one sort of the values, like compaction and merging is better. Then also here, we're talking about if you want to find a key in the file, you no longer need to keep an index in memory. You don't need to do that because the offsets for key and handbag and handsome. And because of sorting, that handiwork must appear before those two. That means you can jump to the offset for handbag and scan there until you find handiwork, right? So I'll highlight this part as well. So searching is better, like in an SST, because of the way that you can kind of make ranges work. So I'll also highlight this part too. Well, that you can jump to the offset and scan until you find, so I got that part. So it says you still need to keep in memory index to tell you the offsets for some of the keys, but it can be sparse. One key for every few kilobytes for a segment is sufficient because few kilobytes can be scanned very quickly. So rather than keep every key in, your memory, you just start keeping ranges or rows. And this will help you kind of find stuff faster, which is nicer sorted segment file or an SS table. Read requests need to scan over several key pairs in the requested range anyway. And it's possible to group those records into a block and compress them before writing to disk. Each entry in the sparse in-memory index then points to the start of a compressed block. Besides saving disk space, compression also reduces the IO bandwidth. So these are kind of like the main advantages, right? Like you get like that faster search, easier to compress the data, cheaper usage of memory, and then, just basically like compaction is simpler using this merge sort. So any questions here before I kind of get into this section? Because this is the last one. I think like we're probably going to go over time if we like really go down this part. Was this kind of like an interesting chapter so far?
Yeah. I mean, it's still good. So still got to learn about the in-memory databases and this SS tables and stuff. Yeah, it's definitely useful. You need to find applications for it, which might be hard in day-to-day work, but let's see how much of this knowledge will retain, right, if you don't use. But yeah, I will make sure that I will keep the notes updated on this, especially because it's something that we don't use often. So we need notes to revive our memory.
Yeah, I was just thinking like, just it's crazy how much work has gone to make like, all of these different things that we sort of just can like say now, like, oh, we don't even really care how it works. Right? Like we just kind of like assume that it just works, like databases. And like if you think about like all the components that go into it, things that can be so complicated, right? Like the people who really work on this are really, really smart, especially like if you think about like hash tables, implementing the hash and then moving from a hash to something like a merge sort, and then later to a red black tree or an AVL tree. I mean, like this is just, it's crazy. Like I already kind of feel like data structures and algorithms as a course is pretty hard, but like this is just like to another level. So it makes me have more appreciation for the people who made these kind of things. It's like, wow, like this is like true, like solid engineering, like, all these, thoughts that probably went through their head as they worked to make like the most fine-tuned thing for a very simple application, right? So yeah, those were sort of my thoughts. Just again, like we started off with a simple example and then going through all the fine tunements just to get it to work, just average case well, and then like the improvements that you can make to like make it even more optimal. So I think this is a pretty good chapter on like system designing a database. I guess like in the last few minutes here, like, are you all familiar with trees and red black trees or AVL trees?
Yeah. I think, yeah, if
Awesome.
you went to computer science, you would be forced to learn this.
Good. Okay. I just want to make
I
sure.
don't know. I mean, I learned them in school, and then I never heard of them again.
Right.
So, yeah.
Okay. We'll just review here. Like a red black tree essentially is kind of actually Wikipedia should be okay. It's kind of this tree that keeps track of like positions. Basically, it's a binary search tree where left values that are smaller sit on the left side, and values that are larger sit on the right side. But then if you have a list that is only all left values, then it becomes suboptimal. It becomes searching for stuff in a binary search tree, usually is like pretty fast O log n, because you can just kind of like look for the value. If the value is less than 13, then not to look at, one side of the tree and just go to this. And then, if you're looking for like 7, then you know that it's not going to be on this side, and you can keep going until you find 7 or you don't find it at all. Whereas if you have a long linked list of just lower values, then you need to rotate the tree to find like the newest value. So like a red black tree is kind of like one way of keeping the tree balanced, right? So that it can be a binary search tree. And the idea is that all the nodes like should have the same number of black nodes like for each path. So here you have 1, 2, 3 nulls are considered black nodes, and anything in between can be a red node, but you can't have red children, and you can't have red parents. So this is, just an idea that they use to maintain like the tree's balance stability. There's also AVL trees. And then again, like I was saying, right, like just the implementation part is just, again, like about this rotation. But then, like implementation part is just basically being able to like search for stuff faster than you can in an array, because when you are going through an array, you may have ON searches at some points. Like if, you're going through a hash table, hash tables are backed by arrays in some cases. And if there are too many collisions, then you can have like an ON performance. Whereas like with a tree, you're guaranteed that no matter what, it'll still be like this kind of half and half, basically log of n approach essentially to like finding an element. So that's an optimization here. So it says maintaining a sorted structure on a disk is possible. See B trees, but maintaining in memory is much easier. There are plenty of well-known tree data structures that you can use, such as red-black trees or AVL trees. with these data structures, you can insert keys in any order and read them back in sorted order. So that's another thing you get with the tree too, is that it maintains like the sorted state of your, it maintains like a sorted state of like your data, right? Like all of the left values can be read 1, 6, 8, 11, 13, 15, 17, 22, 25, 27. And that is very easy to get a sorted set of data. It's harder to do that with an array. So for next time, we'll go through the implementation of this and get to, some of the optimizations, and we'll go from there. Does anyone have any questions or anything to add to anything that I talked about here? All right. Well, then, thanks for coming today. And we'll see you all next week. We'll see you on Friday.
Thank you.
Jay,
All right.
anything that you want us to read up ahead so you don't have to talk so much? We can just have, or one of us, if you want us to take over for one session and give you a break, that also works.
Yeah, I'm totally fine if you want to go through this section and then maybe talk about what you got. And then I can also just kind of like sit back with my camera off and, just
yeah,
like not say anything the whole time. No, I'm just kidding.
Yeah, we can give it a try. I don't know how comfortable I would be talking for an hour, but I understand it's a lot of stress on you.
No, it's not. I actually, like I said, I like this. It's not stressful at all. It's fun.
Okay, yeah, let's I will come prepared. I didn't read this chapter ahead of time, so it's kind of not participating too much, but I will read up for tomorrow.
Yeah, just give it a read, and then maybe, I think like as a precursor, you might want to also just kind of review some data structures, algorithm stuff. I'll share this list that like I've been keeping just to keep track of this stuff, because like otherwise like I won't remember it too, like you're all saying, right? Like I just have been making like a cheat sheet of notes. So I'll share this if you want. In fact, I'll just put this on the web. So copy link. And in this way, you can kind of like go through. One cool site that I found was this Big O cheat sheet. And it basically kind of like gives you like time complexity and space complexity of like different data structures and how they compare. And then also the same for the sorting algorithms. So you can see like here again, B tree, red black tree, the stuff that he's actually using in this chapter. You can kind of like see how much it takes for access, searching, insertion or appends, deletions. And then this is average case, right? And then this is worst case. And most people in computer science pretty much go off of worst case. But if you see, like this symbol, the O, that's worst case. If you see theta, then that would be average case. And if you see omega, then that would be the best case, right? If you want to be positive. So I'll share both of these in the chat. All right. Well, thank you all for coming, and I'll see you Friday.
Yeah, are you gonna? You said you were gonna share the Notion link, your Notion link for the data structures too, right?
Yeah, I just did it on Discord, and I'll do it in the WhatsApp as well.
Oh, okay.
So one more time, copy the link. And here we go. And then here is the Big O cheat sheet. And like the other one that I've been using too is this Geeks for Geeks, which I think people know. But it's pretty good in terms of, the only thing I don't like is this forced dark mode. There must be a way to like turn it off. I just don't know. Like I can't figure out the site, but it's pretty good for just kind of like looking up like data structures and algorithms fast. Like if you want to like kind of like see like what a merge sort is, you can probably just search for it in here. In fact, I just kind of use Google and I just say Geeks for Geeks. But like instead of going through like a long video, it's kind of like nice to just kind of go in here and see like a simple example and then try out some code. So this will help you kind of jog your memory pretty quickly. And this kind of gives you like the basic, like pseudocode here. So it's pretty useful. And then of course, lead code, if you want to like actually practice this stuff. So, all right. Yeah, just let me know if you're doing any of this stuff or lead code.
Are you doing the other data structures study group with Jordan and folks?
No, we haven't like studied. Wait, does he have one going, or is it?
No, you were suggesting something, right? Like you're asking for interest.
Yeah, so I just basically started off by asking if people have interest. I know Karthik is interested, but he has some stuff to do until like middle of May. Is that correct?
Yeah, I just have some travel to Seattle. Yeah, after May I should be available. Sort of.
Okay. And then I have a friend from my work days. His name is Sam White, so he might be interested in that. And then I think I have another friend who's interested. So at this point, I have 3 people, and maybe yourself, Amelia. So we could start this if y'all want to get into it. Just let me know.
Yeah, I have some India plan. I have India plans, and so I would be interested. Maybe if it's a long running thing, then I'll just join you guys later. But if it's just first like some goal oriented, you want to do an interview, then you'll probably be done by the time my summer vacation is done. So, I would be back in August. Maybe that's too late for folks. But yeah.
So I'll just share this quickly. Like, this is kind of like my like work notebook, just to kind of, keep on top of like my own personal goals. But like, I have like this thing where, I'm trying to go through each month, basically until like, I feel like, I should probably get paid more, right? So 2023, it's probably like my own goal, but like, so I'm right now here at May, I'm saying that I want to do data structures and algorithms and system design. So like, that's where my focus is. And I'm just doing this pretty much like until, until I get bored of it and I'm like really good at it. Right. But essentially like, I would only know I'm really good at it. Like if I'm doing well at those leak code problems and probably like answering like some of these, interview questions really easily. But yeah, so I have a lot of time to do this. I feel like maybe the structure for building this group might be a little different than like doing a YouTube video. So like system design and like studying over video on YouTube is cool, but I think like maybe for data structure and algorithms, it might be more of like a pairing session, like one-on-one, or it might be like 2 people kind of, like watching somebody else whiteboard, and then just contributing, or maybe just like we all kind of work together and keep like a GitHub repo together of questions that we've solved. And then we can kind of like code review each person's, progress. So that's kind of like my idea. I'm just playing around with the formats at the moment. I don't know which one makes the most sense. So I'm open to hearing about what you all think. Just kind of like maintaining a repo, or maybe like doing a pair programming session, or whatever have you. All right. Did you want to say something, Ramya?
I think for algorithms, the velocity of solving the problem is also important in an interview setting. So I don't know if there are webs, apart from lead code, where there are, you can practice, but you can also time your code to completion. So that's because.
So there are 2 sites that I know about. One that's called Pramp, and then there's another one that is quite similar. So Pramp and then interviewing.io. But people choose this stuff because you get like a real person from Fang on the other side, but you have to pay for it. In my mind, I was thinking, why don't we just make up this on our own? Because you don't really know who is behind the screen, but we could pretend to do the same thing for ourselves.
Yeah, makes sense. Yeah. Also, like a portal, I don't know if LeetCode already has a timing which you can turn on. Okay, this question needs to be solved in 30 minutes or under 45 minutes. I don't know if there is a portal already, non-human. The other side, it just pops a question with the timer and you're supposed to solve it in 30 minutes. Maybe you can have some other human pairing with you so that you're vocal during your interview process.
So so how is this? So I don't know, at Amazon at least, right? In the on-site interviews, the expectation is not for you to write absolutely compilable code. I think for the first step where you clear the whatever the coding challenges they give you, you need the skill, but later on, the on-site, you just need to be able to talk through a solution and write some not pseudocode, but some syntactically correct code, but it doesn't need to compile or anything.
Everywhere it's the same. Yeah, as long as pseudo is there, it's good enough. If you can explain, right?
Yeah, maybe. So I think the timed thing matters for the first step, right?
Right. And then there's these things, right? Like as far as like working together, I mean, you can use like these online coder pads. And so we can both like edit at the same time. You know, I could put up like a little timer on my desktop and we could watch it if you want, you know, like as it goes down. But just stuff to practice, you know. Like some of the people that I talked to also said that they wanted to just practice like, you know, general questions as well. So like, you know, these questions I've got like React and then JavaScript, you know, so we can do that as well. But yeah, just
in at least Amazon, right? There is a section of interview that focuses on your coding practices, like how well you know the coding, like whatever chosen language you choose, whatever language you choose. So they ask you to write maintainable code, like code that follows, you know, best practices and write programming constructs and stuff like that. So most people do well because the data structure well in data structures and don't do well in the other
languages,
because data structures are it's all streamlined, right? People know exactly what to expect and what kind of questions. So the expectation is set there, but the coding patterns, almost that is kind of the determining factor whether at what level we should hire the person. So that's amazing.
So you're referring to like the style guide, because I remember like this was kind of something
they would give you a style guide. Yeah. So all of these programming practices, right? Like they would give you some question. Like recently I was shadowing an interview. So one of the questions they were asking was exception handling library. So somebody was asked, write exception handling library in Java. So the expectation was to write some code and using generics and, you know, functional interfaces. So we interviewed like about five people. Not one person was able to write.
Oh wow.
Yeah. Is it more like design patterns? Anti-pattern and
basically see design patterns is one thing, and knowledge of what Java, you know, newer versions are offering, and kind of familiarity with the programming language that you say you are familiar with, right? So
okay, good points. Let's continue like having those discussions on the Discord and the WhatsApp, and maybe just provide some links as well, you know, in terms of how to prepare best for those kind of interviews, because I think it'd be great to just have a complete, you know, preparation thing going on, you know. So, all right, this is the last time I'm going to say it today. But yeah, thank you all for coming, and then we'll see you all Friday.
See you. Bye.
Bye.
Okay, bye everyone.